welcome to lecture 19 of Fox. And look who's here, Orange Malik. And that's because today we're going to be talking about the expected value. Perhaps the most important quantity that we like to compute when it comes to analyzing complex experiments with random complex outcomes. Okay? And the expected value, in some sense, continues our discussion from last lecture. So let's recap. Okay? So last time, we were analyzing complex experiments with complex outcomes, and then we said, well, we're typically not interested in the complex outcome. We're interested in some quantity of interest, a measurement. Okay, and so we introduced this notion of a random variable which captures this intuition of a measurement. For example, if you flip 20 coins, we're not interested in the exact flips, the exact outcome of the 20 coins. We're just interested in the number of heads. Okay, so that's an example of a measurement. It takes on some values, in that case 0, 1, 2 up to 20. Okay, and for each possible value of this measurement, we can compute the probability, and that gives us the probability distribution function for that random variable. So to summarize, a random variable captures a measurement. Okay, it takes on some values, and each value has a probability. And once we have the random variable of interest and its probability distribution function, we can, in some sense, get rid of the complex probability space and work only with the random variable. Okay, and last time we discussed some important random variables: the Bernoulli indicator, 0 or 1 random variable; the uniform, where all the possible values are equally likely. Now, in practice, most experiments don't produce uniform outcomes. Okay, values which are equally probable. But the uniform random variable is extremely powerful in computer science as a way to get algorithms to work by injecting somehow this uniform random variable, in some sense, to break ties, to break conflicts. Okay. Then we talked about the binomial random variable, very important. You're trying something, some fixed number of times, let's say n times, and you're interested in the number of successes. So there's some success probability. You independently try n times. How many successes will I get? Okay. And then related to that is the exponential waiting time. Okay, so here you're trying something with some probability of success, and you will keep repeating until you succeed. Okay. And we're interested in knowing how long will it take to succeed. Okay, so that's the measurement that we make from that experiment. All right, and so both of those, the binomial, so where you try something n times and count the number of successes, and the exponential waiting time, where you try something until success, those are very commonly occurring experiments in practice. Okay? And we discussed several examples. For example, a couple having kids until they have a boy, sending an internet packet, sending a packet through the internet until it succeeds. Okay? Guessing randomly on a 15-question multiple choice test, and so on. Okay, so it's important to be able to recognize these random variables. But today we're going to further summarize the experiment. Okay, now we've already summarized the experiment to the quantity of interest, the thing that we measure. Okay, and we have reduced that thing we measure to this random variable and its probability distribution function. And now we would like to further summarize, and that further summary is think of what do we expect to happen. Okay, so now you run the experiment. Yes, you can measure the temperature. Yes, you can measure the number of heads. But what do we expect to find when we run this experiment? Okay, and that is the expected value. Okay, so it further summarizes the experiment by computing the expected outcome for the random variable, for the measurement. Okay, and so we'll discuss a bunch of examples, starting with flipping coins, dice, and then we'll go to these 4 random variables: the Bernoulli, the uniform, the binomial, and the waiting time. And finally, we will talk about conditional expectation, okay, similar to conditional probability. Okay, and that'll introduce us to the law of total expectation, a very important law, just like the law of total probability, that allows us to compute expectations more quickly, and also it allows us to compute expectations using a build-up method. Okay, so let's talk about expected value. Let's go to the board. Let's start with a simple experiment. Flip 2 coins, and we know the probability space. Okay, so flip 2 coins. Okay, and so what's the probability space? Well, the sample space of possible outcomes are HH, HT, TH, TT. Okay, and we know the probabilities is this uniform probability space. You can compute it with the outcome tree. Okay, so the probability for an outcome omega is 1/4, 1/4, 1/4, 1/4. Okay, but now we're not interested in the specific outcome. The quantity of interest for us is the number of heads. So this defines the random variable. So the random variable, which is the number of heads, okay, is 2, 1, 1, 0. And so what this random variable does is it converts our original probability space to something like a new probability space. It's the possible outcomes for the random variable and their associated probabilities, the PDF. So x of omega, so the possible outcomes for the measurement for the number of heads is, it's either 0, 1, or 2. Okay, and the probabilities for each possible outcome, each possible number of heads. And we usually, if we want to be very precise and, explicit in what's the random variable, this is the probability distribution function for the random variable x. And it tells you the probability that the outcome, the measurement is, little x. Little x is 0, 1, 2, 0, 1, or 2. Okay, so then the probability of 0 heads is 1/4. The probability of 1 heads is 1/4 plus 1/4, so 1/2. And the probability of 2 heads is 1/4. Okay, so this is, the experiment, and this is the summary in terms of the random variable. Now, let's talk about the expected value. And the expected value has to do with, repeating the experiment many, many, many times. So let us say we repeat the experiment, I don't know, let's say 12 times. Okay, and here are the outcomes we got. So we're going to get outcomes. Okay, so the outcomes we got are, HH, TH, HT, TT, TT, okay, HH, HT, HT. Okay, so what's that? 1, 2, 3, 4, 5, 6, 7, 8. Let's do 4 more outcomes. Okay, HH, TH, HT, TT. Okay, so we did this experiment 12 times in this example, but think about doing it many, many, many times, and for me on the board, many, many, many times is 12. Okay, so now let's see what my random variable, my measurement, equates to for each experiment. Okay, so here I have 2, here I have 1, 1, 0, 0, 2, 1, 1, 2, 1, 1, 0. Okay, so you see each time I do the experiment, I get a measurement, okay, and so I'm getting a value for my random variable x. And now we might ask, okay, we've done this experiment many, many, many times. What's the average value for your random variable? What's the average value for your measurement that you observed? If you did this experiment many, many, many times. Okay, so let's compute the average. So the average value of x. Okay, let's compute this average value. Well, what do? We add it all up. So 2 plus 1 plus 1, 2 plus 1 plus 1 plus 0 plus 0 plus 2 plus 1 plus 1 plus 2 plus 1 plus 1 plus 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 12 outcomes, okay, we add them all up and divide by the number of times we did the experiment. That's the average value of the observed, number of heads, the average value of the observed measurement, the average value of x. Okay, so we have to divide by 12. So let's add it up. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in this example, it's 12 over 12, which is 1. Okay, good. Now, let me show you another way to compute this average, and that's going to be key. Okay, so what I'm going to do is I'm not going to change the outcomes. I'm just going to reorder them so that something interesting pops out. Okay, so I'm going to start by seeing which outcomes are TT. So I have 3 TTs. I'm just reordering the outcomes. So I have TT, TT, TT. Okay, now let me put the outcomes that are TH or HT. Okay, TH, HT, so TH, HT, 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 okay, and then TH, HT, TH, HT. Okay, then let me put the outcomes that are HH, so HH, HH, HH. Okay, so HH, HH, HH. Okay, very nice. Have I changed the outcomes? No, I've just reordered them. Okay, and you'll see why I reordered them in this particular way. So let me write down now the measurement for each outcome, and you will observe that the measurement is 0, 0, 0. Okay, 1, 1, 1, 1, 1, 1. What's the measurement? Number of heads. 2, 2, 2. Anyone see how I've reordered the outcomes? Okay, cute, right? I've just reordered the outcome so that all the outcomes that have the measurement 0 came first, then all the outcomes that had the measurement 1 came second, and then all the outcomes that had the measurement 2 came third. Okay, just reordering of the outcomes. Okay, but now this allows me to, in a clear way, identify 3 groups of outcomes, one corresponding to the measurement 0, one to the 1, one set of measurements for the 1, and one set of measurements for the 2. Let me call the number of these measurements that appeared, n sub 0. Let me call the number of these measurements that appeared n sub 1, and let me call the number of measurements that appeared here n sub 2. Okay. You might say, why am I doing all this? Wow. Okay. And that's because I want to show you another way to compute this average value. Okay. The average value of x, okay, is equal to the sum of the measurements. Okay, I'm not going to change anything. It's the sum of the measurements. And here I just added them up blindly. Okay, well, I can add them up in a smart way. Okay, if I'm computing the sum, I can take the number of them that are 0 and multiply by 0. I get n0 times 0 plus the number of them that are 1 multiplied by the value 1, which is what they are. Okay, plus n1 times 1 plus, okay, the number of them that are 2 multiplied by the value 2. Okay, n2 times 2. Because look, this guy's contribution to the sum is n0 times the value. It'll contribute that many zeros. This will contribute n1 ones, so that's n1 times 1. And this will contribute n2 twos, so that's n2 times 2. Okay, that's another way to write this sum. And okay, I'm going to divide by 12. Okay, 12, which is the total number of experiments. Let me call the total number of experiments n. Okay, and I'll fill in the values right now. Okay, I'll fill in the values. So this is 3 times 0 plus 6. So there are 6 n1. Okay, so n0 equals 3, n1 equals 6, and n2 equals 3. So 3 times 0 plus 6 times 1 plus 3 times 2. Okay, over n, which is 12. 6 plus 3 plus 3 is 12. Okay, so now what do I get? I get 3 times 0 is 0 plus 6 plus 6. So which is 12 over 12. And no surprise, I get the same value, 1. So let me box it. Okay. So in this case, I got the value 1. And in this case, I also got the value 1. And it's no surprise. I didn't change the average. I just changed the way I approach the calculation of the average. Okay. And now, okay, this is the interesting expression that I want to focus on. Because if I break it down, what I get here is I get n0 over n, n0 over n times 0, which is the value of x that corresponds to all those outcomes, times 0, plus n1 over n, n1 over n times 0, plus n2 over n times, n1 over n times 1, the value of x, times 1, plus n2 over n times 2. Okay. And now, okay, while I only did 12 experiments, okay, imagine that we did many experiments. N is a million, a billion, a trillion. Okay. Well, by the frequency interpretation of probability, okay, the number of times you see 0 as your measurement divided by the number of times you did the measurement is exactly what we interpret as the probability to get the measurement 0. So this here is exactly p sub x of 0. Okay, the PDF is coming in, and this here, n1 over n, is exactly p sub big X of 1, the PDF at 1. And this here is exactly p sub big X at 2. Okay, and so this is exactly equal to 0 times px of 0 plus 1 times px of 1 plus 2 times px of 2. Okay. And now using a fancy summation notation, this is the sum over the possible values of x. Okay, we can even be explicit. It's from x equals 0 to 2 of x times p big X of x. Okay. So, this is equal to this. This, let me write this as, it's what the frequency interpretation of probability tells us. So we expect this to be approximately equal to this as n becomes larger and larger. This is the frequency interpretation of probability. Okay? And so, what I have here is now a formula which I can compute directly from this PDF table. And what does this formula compute? It computes what I expect to see as the average measurement if I run the experiment over and over and over many, many times. So here we have a formula for what would happen if you run the experiment many times. Okay? And let's see what this formula says. What the formula says is that, this formula is equal to, 0 times 1/4, 0 times 1/4 plus 1 times 1/2, 1 times 1/2 plus 2 times 1/4, 2 times 1/4. So 0 plus a half, which is 1. And indeed, that's what we happen to observe in this experiment, but that's because I constructed the experiment. Okay. Now, indeed, okay, here's an experiment you can actually do at home. Okay. Run this experiment many, many, many times. Flip 2 coins. You can even do it on your computer. Flip 2 coins over and over and over and over and over and over and over again. Not 12 times. Okay. Try to do it 1,000 times. Okay. Do it 1,000 times. Each time count the number of heads and then take the average of all the heads you got. Okay. And see what the result is. It should be very close to 1, because that's what this formula is approximating. Okay. So, summary. Okay. And now we can generalize this formula to a general PDF, and that's what the summary is going to be. So, summary. Okay. So I'll now summarize even the derivation. If you have a random variable, x, okay, that takes on values, okay, and we'll generically represent the values by little x, okay, generic value, okay, with probability px of x. So this is little x. So this is the PDF of x. Okay, so you have a random variable x, which takes on values. Okay. When you run an experiment, okay, and you measure x, you get some value. Okay. And if you run the experiment many, many, many times, okay, so run the experiment many times, measuring x. Okay, so you run the experiment many times and you've measured x. Okay, so you get, let's say x1, x2, x3, up to xn. So you run the experiment n times. Okay, so you run the experiment n times. Now, when you compute the average is equal to the sum from I equals 1 to little n of xi divided by n. Okay, the sum from I equals 1 to big N of little the measured values divided by n, and this is going to approximately, so this is the first way of computing the average. This is going to be approximately equal the second way of computing the average, which is the sum over the possible values x of x, px of x. So this is the result of the actual experiment. Okay, so this is the result of the actual experiment. And this is a formula involving the PDF, which is what we derived here in this special case. Okay, now if you do the general case, you will find, okay, so n0, so let's say x can take on the values of 0, 1, 2, 3 up to, let's say, 100. So you will have n0, n1, n2 up to n100, and you'll count up the number of times you've got outcome 0, then outcome 1, and then outcome 2, and you'll have a formula like this in the general case, and you'll divide by the total n, and each of these ratios, n sub n0 over n, n1 over n, n2 over n, n3 over n, and up to n100 over n, they'll all approach the corresponding probabilities in the PDF, okay? And then they're multiplied by the corresponding value of x, and so that's what this formula is doing. Okay? So, this is a miracle, because it would take a very long time to do a billion, a million, a trillion experiments. But computing this formula may not take a long time at all. It's just a formula that involves the PDF, and we're going to see very many examples. And so, as in lieu, instead of doing the experiment a billion times, we can just compute the formula, and we know what the average will approximate if you were to do the experiment many times, and measure the random variable, measure the quantity of interest, and then take the average of those. Okay? So we have a formula that we can use to sort of compute that average ahead of time. And that's a very useful average to know. It says that if you were to repeat this experiment many times, that's what you'd see on average. It tells you in some sense what to expect from the experiment. And so we define this formula as the expected value of the random variable. So definition. Expected value of the random variable x with PDF p sub x is, okay, the sum over all the possible values, okay, of the value that it could take on times the probability of taking on that value. Okay. And there are many ways that people refer to this formula. They say it's the expectation, it's the expected value, the mean, okay, the average. Okay. And now we're going to do lots of examples. So I'm going to box this summary because it is very important. It's like a miracle. Okay. I have a formula that I can compute, okay, which tells me if I repeat an experiment many times, on average, what will happen. It's a formula. Okay. And let's start with this example. Okay. We already did it, but let's just repeat. Okay, so now let's erase all this. Okay, examples. Okay, so first example. So for this random variable, the number of heads when you toss a coin 2 times, the expected value, and so typically we write here, the expected value of x is equal to. So the expected value of x. Okay, so let's box this. You know what the box says? Box says, do not erase, Malik. Okay, sometimes, as some students have pointed out, even the box cannot resist the speed erase, but we will try to resist erasing that. Okay, so the expected value for this random variable is, so what you do, okay, if you want a sort of a prescription, you take the possible values, multiply by the corresponding probabilities, so multiply, and then add. That's all it is. It's a formula. Okay, so let's do that. Okay, so the expected value, multiply the possible values by the probabilities and add. So 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4, which is equal to 1. So on average, when you run this experiment, you expect to see a 1 on average. Okay. Let's do the next level of complexity. Flip 3 coins. Flip 3 coins. Okay. So now the sample space is a little more complicated. It's H, 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 T, H, T, H, H, T, T, H, T, H, H, sorry. THH, THT, TTH, TTT. So that's the sample space. Now it's gotten a very complicated sample space. And you can do the outcome tree and get the probabilities. Okay, it's a uniform sample space, so the probabilities are 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. No surprise. And when you compute the random variable, which is the same random variable, number of heads, okay, so x of omega, so the possible values are 0, 1, 2, 3 now. You can have 3, and the probability p sub x of x, okay, and the probability of 0 is 1/8, okay, 3/8, 3/8, 1/8, okay. So there you have the probabilities, and we can ask, what is the expected number of heads when you flip 3 coins? So the expected value of x is equal to, well, we can use the formula. We derive the formula, and the formula is relatively simple. You take each possible value for x, multiply by the probabilities, okay, and add. So 0 times 1/8, 0 times 1/8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. Okay, so what is this? Let's do the addition. Okay, so you get 0, you get 3/8, plus 6/8, plus 3/8, okay, which is 12/8, which is 1.5. What? What use is this formula? Okay, because it seems to say something absolutely bizarre. Okay. When you run this experiment and flip 3 coins, okay, the expected number of heads, and I'm reading this as, you know, we would typically read it, the expected value for the number of heads, or sometimes we just say the expected number of heads is 1.5. And you say, what? The expected number of heads is 1.5? That's not even possible. Okay, and so this is where we have to come back to the definition of the expected value, and what is it capturing? Okay, what it's capturing is not the typical number of heads you will see. It's not even the case that the expected value is possible. It's never possible. You flip 3 coins, I guarantee you will never see 1.5 heads. Okay? So in some sense, it's not what you expect to see. Okay? So it's important to sort of realize that what the expected value captures is not what you expect to see. It's not what you will often see. It's not what you will typically see. It is the expected value, which you must think of as an average. Okay, so what this is saying is that when you flip the coins many times, sometimes you'll get 0, 1, 2, 3, 0, 1, 2, 3, and so on. And we take the average of all those, it'll be 1.5. Okay, and that just means that the average of the number of heads you see, you know, is not one of the possible number of heads you will see, but that's not a big deal. I mean, if you take the average of 0 and 1, the average of 0 and 1, that's 1/2. There's no law that says that when you take the average of some set of numbers, that the result must be one of the numbers you are taking an average of. No. Okay? And this is a property of the average. Okay? The average can take you outside of a set, and that's what's happening here. So it's very important. You know, in your mind, you should think of the expected value, not as a typical value, not as what you expect to see, but as what you would see if you did the experiment many times and then averaged the results. Okay? The point is, we don't want to do the experiment many times and average the result, and we don't have to, because we have this very nice, convenient formula that tells us what would happen if we did the experiment many times, and by many I mean not a billion, not a trillion, 100 trillion, a trillion, much more. If we did the experiment many times, we know what would happen without doing the experiment. We can take the average of the outcomes using a formula, using what's called the mathematical expectation. Okay, so let me give you some exercises. Let's erase this, and then I'll give you some exercises. Okay, so roll a die. And your measurement is the value of the roll, 1, 2, 3, 4, 5, or 6. So what's the expected value of a roll of a single die? Okay, so exercise. Expected value of the roll of a single die. I'll give you 5 seconds, pause the video. 1, 2, 3, 4, 5. Okay, I hope you figured it out. You wrote down the possible values and their probabilities, and then multiply possible values by probabilities and added, and you should have gotten 3.5. Odd. It's the same odd outcome as the expected number of heads from 3 coin flips. You'll never, ever in your life, when you roll a die, get 3.5. Okay, but again, the expected value is not the value you expect. It's not the typical value. It's the value you will get on average if you rolled many, many, many times. Now try it. Roll a die 100 times. Get all the values, average them. You should get something close to 3.5. Okay, a slightly more sort of theoretical exercise. There's another formula for the expected value. So here we focused on the expected value using the PDF of the random variable. We can just use the random variable directly on the sample space. Okay, so show that, okay, and I'll box it also. So exercise. Show that the expected value is also equal to the sum over the possible outcomes in your sample space, okay, of the random variable evaluated at your outcome times the probability of the outcome. Okay, because remember, the random variable is a function. It takes an outcome and produces a value. And then there's the probability of the value. So this and this are very similar. Okay, here, the sum is over the values of the random variable. So this guy is in x of omega. So this uses the PDF for x. This uses x as a function and the probabilities for the outcomes. So you could compute the expected value from the outcome space or from the PDF. Okay? But this is just an exercise. We won't really need this much because that's one of the reasons why we got the random variable, is so that we don't need to go back to the sample space, okay, unless we absolutely have to. Okay, let's do another example. So the expected value here is 1.5. Okay. Let's roll a pair of dice. Now we computed the PDF for the sum of 2 dice. Okay, so sum of 2 dice. Okay, and the possible values. So x of omega, the possible values were, and the probabilities associated with those. So you can go and look up your notes. The possible values when you roll 2 dice and take the sum is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are the possible values. And let me tell you what the probabilities are. Okay, so 36 possible outcomes. This is 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36, 7 over 36, 5 over 36, 4 over 36, 3 over 36, 2 over 36, 1 over 36. So this was the PDF for the sum of a pair of dice. Okay, so if we compute the expected value is of the random variable is just, you weight the possible values by the probabilities and add. So you're going to get, 1 times 2, 1 times 2 plus 2 times 3, 2 times 3 plus 3 times 4 plus 4 times 5 plus 5 times 6 plus 6 times 7 plus 5 times 8, okay, plus 4 times 9, 4 times 9 plus 3 times 10 plus 2 times 11 plus 1 times 12. Okay, divide that whole thing by 36. Okay, so that's the expected value. Okay, and now when you go and do all this, do it in your head if you can. Okay, so you are going to get that the expected value is 7. So when you roll a pair of dice, not only is the most likely value 7, but the expected value is also 7. Okay? So in this particular case, the expected value is one of the possible values and happens to be the most likely value. But what I really did this for was to show you that when we roll 1 dice, the expected roll is 3.5. When we roll 2 dice, the expected roll is 7. And you might spot a pattern, a single instance of a pattern here. So can anybody guess what would happen if we rolled 3 dice? Pause the video. 1, 2, 3. Coming back. If you guess 10.5, wow, you are very good at spotting patterns. Okay, so that's just related to something we will discuss next lecture. Okay, but I just wanted to point it out to you. Now, let's erase and do the expected values of our common, our famous binary, random variable, the uniform, the binomial, and the expected waiting time. Okay, and for those experiments that are common in practice, and that will also illustrate some interesting, cute little techniques for computing sums that are very useful to tuck into your bag, and perhaps you might find use for them some other time. Okay, and then we will talk about conditional expectation. So let's erase. Speed erase. Avoiding the box, the infamous box. Bam, 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 bam.